Hi, I'm Mike Stanzik and welcome to Digital Electronics Classroom. In today's video we're going to be talking about sequential circuit analysis. We're going to introduce some terms. We're going to start with the circuit diagram itself, and then we're going to, from that, derive what's called the state equations or the input equations that we have for our system. And then we're going to build a state table, and we'll introduce the state table. And then finally we'll make a state diagram. And so these are all new terms for us, and so we're going to define them in an example. And I think that will be the most use for us. We're going to do the simplest design we can, so we're going to use D flip-flops. And I'll mention how that is going to benefit us while we're going through that design. But this is going to be a little bit of a longer video, and it might be one that you need to watch maybe more than once to get the full gist of what's going on. Okay, so get buckled in and let's get started. So what you see here is a circuit diagram, and we're going to be doing, it's a sequential circuit analysis. And in the sequential circuit analysis, we have a path. We go from the circuit schematic, the diagram, we go to the state equations, and then we go to the state table, and then we end up with the state diagram. And this is the opposite for when we would do sequential circuit design, when we have an idea that we want to implement. In this case, this is something that's already implemented, and we want to say, well, what does it do? And so this is the process that we're doing right now. Okay. So the first thing I'm going to do is take this schematic that's given to us, and I'm going to generate the state equations. Now this is where it's a benefit to have a D flip-flop, because whatever comes into the D is going to be passed along to the output. So it's a transparent flip-flop, if you will. Whatever is present on the input line when the clock triggers, that will be pushed to the output, and that'll be the new output. There's also, we're going to be feeding back these A's and these B's and also their complement. And so we have to understand the difference in our terminology of whether we're looking at a present state A variable or a next state A variable. And so our convention is that if you write A of t plus 1, time plus 1, this is signifying that it's next state. Okay, and then if it's just A, then that's the present state. Okay. So when we write our expressions here, I'm going to write them in the form of A of t plus 1, so the next state of A is equal to something. Now we just use our combinational logic. And so I've set this up here so this is fairly easy to read. There's this bus of wires here. We got A bar, B, and B bar, and they're coming from the flip-flops. There's A bar, there's B, and there's B bar, and I've just routed them around in this way. This is not typically what I would do, but I'm doing it this way because I think it'd be easier for us to see. The other thing, and I didn't kind of do the overview of the circuit here, to notice is that we have an input X, and then we have our two internal memory elements, and we're calling those A and B, and then we have an output Y. And so we're going to generate an expression for A, B, and Y. So A next state, B next state, and then Y itself as the output. All right, so let's look at A next state. So in here I have A coming in, and I have B bar coming in. So this is going to be A and B bar. And then I have the B bar is also going into that second AND gate, and X. And so we have B bar X. So this is the state equation for the A flip-flop. And so whatever these values are, in the next clock cycle, that will become the new state for A. Let's do B. B of t plus 1. So what does the combinational logic say for the input to the B flip-flop? Well, it looks like here we have an A and an X bar. Excuse me, a little something in my throat there. And then we have here, we got to make sure we're following the lines down correctly. So that's B and also X bar. So AX bar or BX bar. And then we're going to write one for Y. Y here, looks like we have A going into Y and X bar. Now you might say that's the same term as the one above. Why do we make a separate circuit for it? I'm just trying to keep things really simple. We're not going to take any shortcuts here. We're going to do it procedurally, step by step. And so I didn't make it simplified, just kept it the way it was, okay? And so then we have A bar and X. Great. So these are our state equations. The next step is to take these state equations and then put them into the state table. So here's our state table at the bottom here. So let me just kind of highlight that these are the state equations, and this will be our state table. Okay. And so the state table acts a lot like a truth table, in that we are going to look at all the possible combinations of something and then look at what happens to another set of variables. The difference is that what we look at as combinations and what we look at as kind of the outputs, the inputs and outputs, are different. So we have this present state is going to be represented by these first two columns. And so we're going to go ahead and put this as A, B, and then the input, X. Okay. And then we have our output columns, and the output columns are going to be the next state, A and B, and then the output, Y. Okay? And so that's what we have here. So let's take a look of how we fill out this truth table, or this state table. So we're going to do it just like we would do any other truth table. So I look at what A's next state is going to be, and it's A, B bar. So first, this is sum of products, and so we know how to fill this in. Anywhere that A, B bar is true, then we'll put a 1 in the output. And so when A is 1 and B is 0. So A is 1 of these last 4, B is 0 for those two. Now we have B bar X, where B is 0 and X is 1. B is 0, X is 1 here. B is 0, X is 1 here. That's redundant. And then all these are zeros. Okay, that's all there is to it. And so we'll do the same thing for B. A X bar, so when A is 1 and X is 0. And so we have a 1 here and a 1 there. And then BX bar, so when B is 1 and X is 0. B is 1, X is 0 there. B is 1, X is 0 there, but we already had that one. So we have this. And then Y is AX bar or A bar X. So when A is 1 and X bar is 0, or X is 0, sorry, which will be right here and right here. And then when A is 0 and X is 1, which is right here and right here. So we have this. Okay, fantastic. So now we have our state table. This is our state table. And it says this. It says, hey, if you're in the present state 0, 0, so A is 0 and B is 0, and the input 0 comes in, and then the clock transitions, what's going to happen? Well, the next state for A and B is going to be 0, 0 as well, and the output should be 0 at that point. If I start with a state of 0, 0 and the X input is 1, then A will turn to a 1 in the next state, and B will remain a 0, and then we'll also have an output of 1. So this is telling us how the circuit behaves in time as we go from one clock cycle to the next. What changes about the output? What changes about the internal state? And that's what that state table is telling us. So let's look at the state diagram. So I need the state table to build a state diagram, so I'm just going to kind of roll it down a little bit there. and we'll build it right underneath it here. So first off, how many states do we have? Well, if we look at the number of states, the number of states is going to be related to the number of flip-flops, right? So if we have n flip-flops, we have 2 to the n states. So I don't know why I drew that number there. I'm just going to write it, number of states. Okay, so n flip-flops gives us 2 to the n states. And so in this case, how many flip-flops do we have? We have 2. So 2 to the n would be 4 states. And so I can draw a circle for each state. So circle per, sorry about that. I'm particular, so even though my handwriting isn't great, I like to make sure it's legible. Circle per state. And so let's draw those circles. So there's 1, there's 2, there's 3, and there's 4. And so then I'm going to label each of these with an AB value. So 0, 0, 0, 1, 1, 0, 1, 1. Now it doesn't really matter how you've labeled them or any order. We're not going for that at this point. We just want to make sure that each of the possible combinations of A and B are present in one of the circles. Okay. So now we look at what happens from the present state to the next state and the input and the output. And what we're going to do is, so look like this, right? So we got AB, that's going to go to AB right here. So 0, 0 will go to 0, 0. And so we're going to draw an arrow to represent that. So I start at 0, 0, and I end at 0, 0. So that's a state transition to the same state, okay? So that's the first thing that I want to do. The second thing I want to do is I want to mark what the input was and what the output was during that transition. And I'm going to do that in this way with a little slash in between. And so this is going to be, you know, so if I have 0, 0, this is the input, and this here is the output, Y. Okay. All right, so that's how we do it. Now we're just going to do every other row in this state table. And so, you know, if you're feeling comfortable with it, go ahead and start doing it on your own. I'm going to use, I think, red for all the arrows, and then I'll do green for the number, the inputs and the outputs. All right, so let's look at the next row. So 0, 0 goes to 1, 0 when there's a 1 input. You know, maybe I'll just do red for all of them, just I think because we got it here. A 1 and a 1. So 0, 0 is going to go to 1, 0. And we typically, you know, give a little bit of a curve here. And so in this case, on this transition, there was a 1 input and a 1 output. Now, 0, 1 is going to go to 0, 1. So I'll make a little loop. And that happens when X is 0 and output Y is 0. 1, 0 is going to go to 1, 1. So 1, 0 is going to go to 1, 1 right here. And that happens when X is 0 and Y is 1. And I skipped one. 0, 1 is going to go to 0, 0. So it's going to do that. And that happens when X is 1 and then Y will also be 1. Okay. And then we have 1, 0 is going to go to 1, 0. So we have a little loop loop. And that's when X is 1 and Y is 0. And then we have 1, 1, it's going to go to 0, 1. That happens when X is 0 and Y is 1. And then 1, 1 is going to go to 0, 0. And that happens when X is 1 and Y is 0. So this is our state diagram. And one thing that I want to point out to you is that each of the circles is going to have 2 arrows leaving it because we have 1 input. and that input can be a 0 or a 1. So if I look at 0, 0 right here, it has this arrow leaving it when the input is 0, and then the output, because of that transition, is 0. And when we have this arrow leaving it is when the output is 1. So each of these have 2 arrows leaving it. So this Y output here, what's it supposed to be? Did I just put Y? 1, 0 to 1, 1 on a 0. 1, 0 to 1, 1 on a 0. This should be a 1. I think I just put a Y there. Let's make that a 1. Or a big block. There we go. You guys understand. Okay, so if I look at all of them, I'll see 2 arrows are leaving each of our states, and that's because we have 1 input. If we had 2 possible inputs, we had 2 like an X or W and an X, then we'd have 4 arrows leaving each of our states, which would get kind of a little bit wilder. Okay, well that's it. Just wanted to introduce those concepts to you. So we've looked at the state equations, we've looked at the state table, now we've looked at the state diagram, and you're on your way to being a sequential circuit analyst by looking at these yourself. Next time we'll look at how we do some design, and maybe we'll throw a JK flip-flop in there and show you that it can be a little bit more difficult, which I'm sure you're looking forward to. My name is Mike Stanzik, and this is Digital Electronics Classroom, and as always, have a wonderful day.